Kia ora guys, we're going to be having a look at how to do page 64, which is sort of introduced on page 63 of the Walkermaths book. So the whole idea here is calculating Z values. So what we're going to do is we're going to start off by making a model, and we're just going to look at a real quick concept along the way. So we've got the weight for kiwis here, and you can see that it has a mean of 2.598 kilograms. And a standard deviation of SD is 0.47888. Now, do you guys think that it would be appropriate to use a normal distribution to model the weight of kiwis? I think it doesn't really work because remember we have to follow mass. Now the first thing about it is that mostly around the mean. Now is the data mostly around the mean? That's not entirely true, because the data, what does the mean? 2.598 is around about here somewhere, right? And most of the data is actually to the left of it, so it's already failing there. It's asymptotic. I mean, you can always argue that most data is not asymptotic because it cuts off at either end. The other S is shaped like a bell. It sort of is shaped like a bell, but it's mainly failing this as well as the last one, in which it has to be symmetrical. And this is not symmetrical because it is skewed to the right. But what you could do here is we could color it by gender. So if we color it by gender and then maybe we do like a little split by gender here, notice that the weight of female kiwis seems to be fairly normal. Like it looks like it's like a pretty good bell shape there. And then the weight of males also looks fairly normal-ish. I want to stack dots because it kind of looks cooler sometimes. Now, which one's going to be better to model? I reckon females. Let's go with females, kiwis. So we're going to model that today. So before we can do that, what is the mean of females? So the mean of females is 2.914. Actually, we'll just go 2.9 for today. Just keep it easy for calculations so we get some nice numbers. Standard deviation, we're going to go with 0.4. Okay, so let's model that. So we're going to go over here. Now, I've got this one set up for now, but we're going to ignore that. So the mean is 2.9, so we can just enter that in here, and the standard deviation is 0.4. Ooh, a little bit ugly. Let's zoom it out. In fact, let's fix it up a bit, We'll go from like -4 up to maybe 7. And then what we'll do is we will go to -0.05 over to maybe like 0. Maybe we should have 1. Nice. Okay, so we've got this model here for our female kiwis, and as you can see, the mean looks pretty good, and then the standard deviation, it looks like it matches fairly well to our data over here. It's a little bit stretched. That's just so you can fit it in the picture. Just notice how the center is about right at 2. Oh wait, we got it wrong. Oopsies. Female mean is 2.9. Did I put that in? Yes. Okay, cool. So this is a model of the data, but what we want to start being able to do is work out some values for this. Now the problem is this formula is really, really difficult to work with, and it's a continuous distribution, and for any calculus nerds, this function is like insanely hard. Like it's impossible to integrate, I'm pretty sure. Like it's nasty as heck. It gets this error function that pops up, but we don't need to worry about that. So pretty much we've got this table of values, and you get the table of values in the back of your book. No, where are you, table of values? Here. So this is the standard normal distribution. Now the only problem is that the distribution we are looking at is not the standard normal distribution. So the standard normal distribution is a special distribution. So let's have a look at it. And it's called Z. And it's this little red distribution here. So let's let's go over here and I'll write some notes about the standard normal distribution. So we had our first distribution, which had a mean, I think my green pen stopped working, of 2.9. Not into that. I'm going to change it out. Oh, actually I should match colours while I'm here. Eh? So we had a blue one, which is our females, so female Kiwis. And we decided to have a mean of 2.9 and a standard deviation of 0.4. That's what we settled on, right? This is the blue distribution here. But we only have a table of values for a standard normal distribution. So this is called the standard normal. And the standard normal distribution, let's have a look at it. It is centered around 0. So the mean is 0. Mean, oh shucks. Oh, what am I doing? I'm doing window tab, my bad. Mean is 0. And what does the standard deviation look like? Well, it looks like 3 is the point that covers about 99% of the data. So yes, the standard normal distribution has a standard deviation that is equal to 1. This is just the simplest possible normal distribution you could ever come up with. Like 0 is the easiest mean and 1 is the easiest standard deviation. It's like the simplest you can ever come up with. Now, they have names, right? The name of any distribution that we're going to look at, any model that we are going to come up with, we are going to call that random variable x. We're going to name that random variable x. Now, it's a random variable because every female Kiwi is going to come in and have a different weight, right? Every female Kiwi we're going to look at is going to appear somewhere here at random. So that's why this distribution, we're going to call it x, and it is a random variable. Okay? Now, when we look at the standard normal distribution, we give it its own special name because we use it so often. So we call this capital Z. So the random variable, or the name that we give to the standard normal distribution, is Z. And Z is proportional to x, right? Anything that happens on x, we can draw something equivalent that will happen on the Z normal distribution, the standard normal distribution. So let's think of an example. So maybe we want to we're wondering about let's say how many female Kiwis are let's say between 2.9 kg and 3.2 kg. Right? So these are the sort of questions that you will get. Right? So we can draw that on here. So what we're going to do is I've got this little thing set up so that you can put in two values. So the first value is 2.9 and the second value we decided on was going to be 3.2 kgs. And it colors in an area on our X, or our distribution of female Kiwi weights. Right? So any female Kiwi that is in this bound is going to satisfy this. How many female Kiwis are between 2.9 kg and 3.2 kg? Oh, it's a bit misleading. I'm going to change the question to what proportion? Because we're looking at probabilities right now, and we don't actually have like a sample size or anything that we're talking about, so we can't really deal with it. Now, notice I conveniently picked the mean as our starting value, 2.9 kg, and we're wondering how many are between 2.9 and 3.2 kg. So the answer to this question is pretty much the whole area under this curve. Because it's a proportion or a probability, the whole curve would be equal to 1, and we want to know how much of it is shaded out of 1. Now, see how this definite integral here outputs a solution for us. So Desmos is powerful enough to be able to work out which proportion, and Desmos tells us straight away, well, it's 27% of female Kiwis. That's the amount that are inside that shaded region. But we don't actually have Desmos in the external, so we have to use other means to solve that. So what I want you to notice is look what's happening on the standard normal distribution. Whatever happens on this blue one, the proportional equivalent is happening on this red one. Like, it's what we are seeing here is actually exactly the same area that is being displayed over here. So to sort of illustrate that, I'm going to drag B across a bit, and notice how the blue fills in at the same rate that the red fills in. So right now it would be, see how it's exactly 50% is shaded in. So this area is exactly the same amount as that area over there. So let's bring B back to our 3.2 that we decided on. Now, what we need is a way to get from the blue graph over to the red graph. Now, in order to get from the blue graph over to the red graph, what you need to do is you need to move it over by the mean, and then you need to like smush it out by the standard deviation. That's my best way of describing it anyway. So what we're going to do is, I'm going to rub this bit out so we have a bit of space so I can do some working out for you. Right, so pretty much to be able to get from the blue to the red, all we need to do is see how the mean here is 2.9. If we minused 2.9, it would move that whole graph over. So if we minus 2.9, it would go and move over to here. Right? I'm going to go back again. I don't want to confuse you too much. Okay, so that's the first thing we need to do. So to get from x to z, we need to go x minus the mean. Right? So if we want to get to z and we have x, we need to minus the mean off of it. But we're not quite finished. Once we've minused the mean and taken it to there, there's still one more thing we've got to do. We're going to have to divide the standard deviation. So currently the standard deviation is 0.4. If we divide it by itself, 0.4 divided by 0.4 would get us to 1. So then it would smush the standard deviation down to 1. So it transforms our data into a standard normal distribution with a fairly straightforward formula. Let me just readjust that for you again. I should probably use Control Z. Be much smarter. Anyway, right. So we first minus the mean, and then we just divide by the standard deviation. So we can transform any random variable we can ever come up with to the standard normal distribution just by minusing the mean and then dividing by sigma, right? So we can go from distribution to distribution. The other thing that we can do is we can go from value to value. If we're looking at a value on one, we can transform it using these same steps. So any value that it takes, we can just transform it. So let's have a look at that. So let's say I had some value here. Let's say I had, oh, actually, you can totally see it on the picture. The left-hand side of this, see how it transforms to what the left-hand side of this is. And the right-hand side of this, it transforms to what the right-hand side of that is. That's exactly what's happening in this picture. Now, maybe we should do an example. So we were looking at, what two values? Oh, I shouldn't have rubbed them out. We were looking at 3.2 and 2.9. Well, funnily enough, 2.9 as our x value, if we minus the mean of 2.9, that's just going to get us to 0. So that's how what is here, the left-hand side, got to being 0. But let's have a look at the right-hand side. So let's do some substitution. We were talking about 3.2. So what I'm going to do is over here, I'm going to change this out for 3.2. Right? And then the mean was 2.9. 2.9, and the standard deviation was 0.4. So the z value that's equivalent to this x value is 3.2 minus 2.9 is 0.3. 0.3 over 0.4 is 0.754 3/4. So now we have our little z value. Let's have a look at that. So see here, on the red, we would have got 0.75. So we transformed it or normalized it. Now, we're going to do the final step. I'm going to show you how we can find that area using the table in the back of the book. So we've got the z value of 0.75, and notice that our picture perfectly matches up to what this picture does here. Right? See how we've got our red picture, looks exactly like this picture here. It's from 0 up until our z value. So we have that z value, and it's 0.75. So let's just find 0.75 on this. Well, let me just focus that. Oh, no, it's not working. Okay, 0.75. Okay, so we've got 0.7 here, and then all we do is we just go across to 5. So 0.75 is going to be right there, 0.2734. 0.2734. Let's remember that. Okay, so that means 0.2734. So the probability that a kiwi's weight, a female kiwi's weight, which is the x is what we were looking at, is between the values of 2.9 and, what was the other value? 3.2. We've worked out that all kiwis between these two numbers, right, that random variable, is equal to 0.2734. And that is the output that we were getting over here, if you round it, right? 0.27337 rounds off to 0.2734. So that's, yeah, that's a little tutorial on how to standardize from those pages.